What I want to talk about with this problem, or with this style, is that when you're looking at these, this really just means you still have a polynomial divided by a polynomial. What's different now is all of this mumbo-jumbo here. All that means is that the polynomial is written in descending order. Okay, that's all that means. That just means you have a polynomial of a different degree divided by a polynomial of another degree. Basically, it's like this. You're going to have 2x squared minus 4 over x plus 6. Those are two polynomials. They're written in descending order. They may or may not have the same degree. All those different letterings, that a sub m x to the m plus a sub m minus 1 to the x to the m minus 1, that just means it's written in descending order. That just means it's descending order. So don't freak out when you see that. What I want you to think of is just polynomial of nth degree divided by polynomial of nth degree. So it's polynomial of m degree, polynomial of nth degree. So the degrees could be the same, they could be the different. All right? Yeah, it's like going to the joule. Now, each one of these things is going to have a specific rule. And there's 3 rules to this today. The first one is, in order to work with this stuff, you're going to have the x-intercepts will always be at the zeros of the numerator. I'm going to make a running list on the whiteboard here as well. So we're going to have poly of nth degree divided by poly of nth degree. Well, first thing is that the zeros will be at, I'm sorry, not zeros, x-intercepts. Excuse me, wrote that real quick. Your x-intercepts are at the zeros of numerator. I know, I'm going to put down the whiteboard too. So the x-intercepts are the zeros of the numerator. The vertical asymptotes are at the zeros of the denominator because, again, you can't divide by 0. And once we do a couple examples of this, it's actually pretty easy. Vertical asymptotes. Those two are pretty simple. You'll have polynomial of some degree. You have zeros. The zeros of the numerator are your x-intercepts. The zeros of your denominator will be the vertical asymptotes. The next thing that happens is when we start to worry about horizontal asymptotes. When we're talking about horizontal asymptotes, they can happen in one of 3 possible places. And it depends upon the differing degrees. So when they're talking about here this relationship between the relationship between m and n, the nth degree is the numerator, the nth degree is the denominator. You're looking at which one of them is larger, or are they the same? So if the degree in the numerator is smaller than the degree in the denominator, your horizontal asymptote is at 0. If the degrees are the same, it follows the rule that we did yesterday. Remember how we had linear over linear? It was the coefficients. Well, it's the same thing here. If it's x squared divided by x squared, you're looking at the coefficients of the first terms. That's what that means. So these are this part stands for the leading coefficients. Okay, so if it's 2x squared plus blah, 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 divided by x squared minus blah, 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 it would be 2 over 1, which gives you a horizontal asymptote at 2. And the last one is a little bit different. There's 2 parts to it. One of them is listed, the other one is not. We'll talk about that here in a minute. If you have, excuse me, if the numerator has a higher degree than the denominator, there is no horizontal asymptote. But what does happen is that if there is no horizontal asymptote, but we'll worry about this end behavior later on. But if the nth degree is one more than the nth degree, we have slant asymptote. And we'll explain that here in a minute, how to find that. We actually already know how to find it. We just haven't done it in a problem like this yet. You've actually done this step. Oh, that whole idea of showing you guys how to do certain things throughout the school year to use for later on. Why would somebody try to do that to prepare you to do something? Does that make sense if the numerator has 1 degree more than the denominator? If it's like a 4th degree and a 3rd degree, 4 is 1 more than 3. If it's a 4th degree and a 2nd degree, is that work? No, because 4 is 2 more than 2. And that's a lot of thinking. Yeah. And it's really easy when I start throwing examples. I just wanted to use this as kind of a jump point of what to do when, because once you start doing a couple of them, you're like, oh, okay. And it's the same thing. You just replicate the process over and over. All right. Let's look at an example. So we have y equals x squared plus 4x minus 5 over x minus 6. And what we want to work on today is, we're going to work on mainly the setup of what it's going to look like. And then I'm going to explain to you what you would do next in order to find the points of the graph, which it goes by picking values in the domain. Hint. So first thing you do is you go for it and you try to figure out the zeros of the numerator. We're looking for our x-intercepts. Our x-intercepts are going to be located at the zeros of the numerator, which means I have to do what to the numerator? Factor. When I factor it, I get, well, what times what is negative 5? Then I add 2 to get positive 4. How's that? Is that better? Yeah. So if I factor that, I get the terms of x plus 5x minus 1, which means where are my zeros? So my x-intercepts are negative 5 and 1. Be okay with that? My denominator is x minus 6, so that tells me that I have a vertical asymptote. Where? 6, good. It's the 0 of the denominator. The 0 of the term x minus 6 is 6. So far, so good? What's that? No, we're talking vertical. Vertical asymptotes are always at x equal a number. Horizontals will be at y equals a number. Horizontal asymptotes. Now, if you go through the checklist on the horizontal asymptotes, you had 3 things to look at. You had m greater than n, m less than n, and m equal to n. If it was greater, then you had no, but look for slant, correct? That was one rule. If it was less than, it was at 0, I believe. And if it was equal is landed. If it was equal, you would have lead coefficient over lead coefficient. Which of the 3 is this case? M is greater than n. So there's no horizontal asymptote in this case. But is the second degree one more than a first degree? Which means that there could possibly be, well, there will be, I should say, a slant asymptote. So here I know that m is greater than n by 1. So no horizontal asymptote. But there is a slant. And guess how you find your slant asymptote? Correct. Take another guess.
Yes.
There's an S in it. I'll give it to you. You find a slant asymptote by long division. What do you mean? Yeah, because when we get to the horizontal part, then we're looking at one of three cases. Now, when we did long division, remember, it wasn't a very difficult process to do it. It just took a second. And really, the biggest mistake that most of you guys would make with the long division is you might mess up a sign. So just be careful with that. So remember, you want to turn that x into an x squared. So what do you multiply it by? X. So I put it above the x. Yeah, above the 4x. Distribute that across, I get x squared minus 6x. Now, what do I have to do to both of those parts? Subtract. So take the second it is to put the subtraction symbol over both of them. So you subtract correctly. A lot of times people don't put this extra subtraction symbol here, and they'll mess that up. And you get 10x minus 5. What do you multiply x by? To turn it into a 10x. By 10, good. And subtract out. And honestly, the remainder has nothing to do with this problem now. Oh, yes, sir. It was, I wrote it as negative 60, then I did negative 5 minus a negative 60, so it was negative 5 plus 60 then. And that's why I just wrote it like that. I did that old same change opposite thing. But when you get to this point here, the remainder has nothing to do with the problem. What it does, what this allows you to do, is that this is the equation of the slant asymptote. The slant asymptote would be the equation y equals x plus 10. So it looks kind of weird to go with this, but that's what this would start out as. Now, as I start to put this together and I look at it in a graph, oops, ran out of space here. So let's see here. X-intercepts at negative 5 and 1. Vertical asymptote at 6. And then I have a slant asymptote at y equals x plus 10. Okay? Do you guys agree? It's a slope-intercept form. Do you guys agree that my x-intercept would be at negative 10? Okay. Now, wish I had done this. Yeah, try to. It's tough to do this on a smartboard sometimes. Can move everything. Yeah. There we go. Okay. In an imperfect world, it's a perfect-ish system. Now, this is where things kind of get a little bit weird, if they haven't already. This asymptote runs into this asymptote there. Are we okay with that? That asymptote, remember when we did linear equations where we did all the not linear, what was it called? Brain fart. Linear combinations, where you had the parameters, we figure out where all the intersections of stuff were at, and we'd shade and do all that other junk. Well, if the vertical line is at 6, that means x is always 6. If it's hitting a slant that has an equation of x plus 10, what's the y value there where they hit? 16. I know that this ordered pair would be at 6 and 16. Now, here's what's weird. When you have what's called a slant asymptote, and this is going to take a little getting used to, this is why I wanted to start with the weirdest of them all, you're going to see things a little bit differently. It's not that yesterday you guys were able to pick points on either side of that vertical asymptote to get where your curves are going. Here, when you get into it, this curve looks really weird. But what you can do, let's slide back to this side. Where was my original? In that problem, what's your y-intercept? What's your y-intercept there? No? If you have a y-intercept, what's your value for x? 0. So if I put 0 in for that, I get 0 squared plus 4 times 0 minus 5, divided by 0 minus 6. So it's 5, 6. This is kind of a weird scenario. And when we get to slant asymptotes, it's going to be weird to figure out points to plug in. For the sake of argument, with slant asymptotes, you actually have boundaries that do this. It'll have something similar to that up here. Because this curve, I think I have it saved in my calculator. Nope. Minus 6, thank you. It's coming up and dives, and you won't see it until I change the window here. What did I say the slant asymptote was again, guys? X plus 10? Okay. Thank you for catching that. Watch what happens here. There's one part of it, secondary part, and then you get the slant. That's the kind of stuff that we're going to wind up looking at. And slowly but surely. Now, remember, when you guys did conic sections, when we did conics, you did the rectangular box and the diagonals. You know what those diagonals were? Slant asymptotes, because you'd hug your asymptote and come around it. The diagonals were slant asymptotes. The diagonals were. What's different between the slant asymptote and the conic section is because then you had them going left or right, or you had them going up or down. Here, our conic sections are curved. They're off kiltered, if you will. They're off center. You still have them. Okay? They just look a little bit different. Yes, ma'am. from all of this. Yeah. Yeah, when you get to here. Hmm? Yes, ma'am. I can't hear you. When you're worried about slant asymptote, when you do long division, when you have 1 degree higher in the numerator versus the denominator, it's kind of a shortcut thing over time they figured out that that's going to give you the equation, the slope-intercept form of the slant. The remainder had nothing to do with it then. Yeah.
So how do you get the 5
0, 0, 0, negative 5, 5,
Okay.
negative. Let me show you another one that's a little bit easier. Oh, for right now, that's all we know how to do. We'd just be picking points. Yeah. Zero the denominator. Yeah. Yep. Sir. Shh. Guys, I still have more exams to go through. We got time. We need time here. Yeah. We don't. Yeah, you just got to follow the pattern through it, and it's when we get some ones like this, I'm going to make sure that I give you guys problems that have a slant that's a little bit closer in. I just wanted to show you an example of what's going to happen, of how the procedure of getting all of this going. Yeah. They're going to mirror each other. I don't know what those points are until I start picking points. I'd have to pick 7, 8, 9, because it's to the right of 6. Okay, let me try another one. Look at this one. 3x squared minus 13x plus 10 over x squared plus 8. What we want to do here is we start again by going through the list of things that are on our sheet. First thing you do is always find your x-intercepts. In order to find your x-intercepts, you have to factor the numerator. What times what is 30? You add together to get negative 13. Negative 10, negative 3. Good. We have 3x squared minus 3x minus 10x plus 10. Factored wise, it would be a GCFs, or a grouping, excuse me. We get that. And I know I kind of went through that a little quickly because I want to run a little short here. So we factor our numerator to get our terms. Our terms, therefore, then help us to generate zeros, just like they have in the past. So if I have if I have terms at 3x minus 10 and x minus 1, where are my two zeros? It'll be at 10 thirds and 1. So my x-intercepts will be at 10 thirds and 1. My vertical asymptotes. Vertical asymptotes would be located at the zeros of the denominator. Well, in the denominator, I have x squared plus 8. If I try to get zeros in that, what do you get? Imaginary. So will I have any vertical asymptotes? No, I have no vertical asymptotes. Next, I look at my degrees. The degree of my numerator is what? 2. The denominator is 2, so they are equal, like you said. So when the degrees are equal, leading coefficient over leading coefficient, so my horizontal asymptote will be at y equals 3. Okay. So when you start to plot this, we have, there's that, 10 thirds and 1. Well, here's 1. 10 thirds. That's a little bit more than 3, right? So at this point, I just have to take a guess then on picking values in my domain. I'm not restricted by my domain here at all because there's no vertical asymptote. So why not just pick numbers that are easy to work with, like 0? If I throw 0 into that, I get 10 over 8 because you couldn't get away from the buffet. Over 8, ATE. It's nice. It's nice to be able to do that. It's nice to be able to do that. So that's what? A little bit more than 1? Why not pick a number a little bit more to the left? Pick -2. What I'm doing here, guys, is you're trying to get an idea of what this curve is doing. Something funky is happening in here. I don't know what. So I'm going to pick a number in here, maybe figure out what's happening at. I'm going to figure out what's happening at -2. I'm going to figure out what's happening at 2. Here's 1, 3, 4, and maybe at 5. That way it gives me an idea of what this curve is actually doing. By using that, you're able to plot points. And that's the idea here. We're just trying to get some rough idea of a rough sketch of what this looks like. Today, basically what you're doing is you're listing everything out. But my suggestion, because tomorrow you're going to plot points and whatnot, is as you're starting to build where all of this stuff is going on, create a rough idea of what it's going to look like. So that way, when we start plotting points tomorrow, you'll know, okay, I just need to pick points on either side of a vertical asymptote. But in this case, I don't have one, so I have to kind of randomly select a couple of ideas of where things are going. Yeah? Here? Oh, I use 0. Because 0 minus 0, 0, so it's 0. It's just, you're just trying to pick quick numbers. You're trying to use deductive reasoning. What makes this quick? Okay? I got one more before we run out of time here. Got that one. Pretty much. You're just going to pick numbers. No, because you will, because what's going to happen is that this is actually going to plug the asymptotes in town. Probably did something wrong. Yeah. You pick points. You just pick any points. It's not domain restricted. You pick a point to kind of figure out where the curve's going. You have to plot points. Some of them don't. Some of them are just a singular curve. As we get into this, you'll start to figure out why. You have to. So you're plug and chug. Seriously. Look, you'll have to plot points, and I need to get through the shell before we get into why everything else happens. Okay? We got to get to start the shell here. Guys, we're running out of time here. I got through 3 more, or actually 2 more than this. So, again, we have y equals 4 over x squared plus 1. What we do here is go through the process. Is there any x-intercepts? Are there any zeros of the numerator? No. So there's no x-intercept. Is there a vertical asymptote? No. No vertical asymptote. Horizontal? Yes, ma'am. If I set x squared plus 1 equal to 0, my 0 would be at an imaginary. It's not real. Okay? We're always looking for real zeros. This case, my value, my numerator is less than my denominator, so my horizontal asymptote then is at 0. Okay. when you look at this, this quite literally becomes pick points again. Go back to the -2, -1, 0, 1, 2. What happens when x is 0? It becomes 4, right? It does exist, because what's 0 squared? 0. What's 0 plus 1? 1. 4 divided by 1 is 4. Now, what's nice about this style, since there's only just that one value of x squared, if I choose -2, isn't it giving me the same answer as +2? That's where you get symmetric stuff going in. So what's 2 squared? What's 4 plus 1? 5. So at 2 and -2, I get 4 over 5, 4/5. What's 1 squared? 1. What's 1 plus 1? 2. What's 4 divided by 2? 2. What's that? Not necessarily. Not everything is going to be a hyperbola. It depends what you wind up with your brain. Okay. All right. Yes, ma'am. Because no matter what you choose for your next value of x, if I choose 7, I get 49 plus 1. I get 50. 4 over 50 is 2/25. It's getting closer and closer and closer to 0. It'll have a symmetric trend upon the other side. Shh. I just use 0. Why not? I can use it. 0 is an easy number to add and subtract, isn't it? Okay. Okay. Does it change here? Does it change here? It does. You have x squared at the top and bottom. So right off the bat, when you have x squared on top and bottom, what does that tell you? They're equal. So you're going to have, you know right away, you're going to have a horizontal asymptote at 3. Where are your vertical asymptotes? Plus or minus 2. Where's my x-intercept? Bless you. At 0. So when it gets to something like this, notice you get 1, 2, 3 sections that you have to substitute values in to figure out what's going on with the curve. What I mean is, you're going to have to pick values to the left of -2, pick the values in between here, and pick values to the right of it. That'll show you what's happening within all 3 of those different boundary areas. That's what's going to happen as these things become more complex. Yes, sir. Once you start picking values of your x, you'll know where things are. You'll see. Okay. Now, I think I already posted the problems here, but I believe it was not 11 through 22. I'm not mistaken. So this is 9.3. We'll start with that. You're not actually graphing all the way through, but what I want you to do is start labeling everything out. So that way, when you start to plot points, you'll understand why are you picking points within certain regions. That's what we're getting at. You want to plot, just how I was doing those shells, like those last couple. Start plotting your shells, so that way when you have to graph them, you'll know where to pick things. Asymptotes, zeros, x-intercepts are real easy, span asymptotes are needed, and then you'll start to plot points tomorrow.